All right, now we'll move on to the friction force. So, friction is the name of the force exerted by a surface that opposes the sliding of two surfaces. So, we're going to use the word sliding as when two objects are moving relative to one another. Friction is always parallel to a surface and it is directed to oppose the sliding of the surfaces. The first type of friction, called static friction, is what occurs when two objects are at rest relative to one another. And what static friction does is it prevents the objects from sliding to begin with. So, to determine which way static friction points, just say, if static friction wasn't here, which way would the sliding occur? And static friction just opposes that. So, for example, if I have a book attached to a wall, if there was no friction there, the book would definitely just start sliding down the wall, right? Friction is what's sticking this to the wall. So that means that friction must be up, because if there wasn't friction, downward sliding would occur. Kinetic friction, on the other hand, is friction that occurs when sliding is actively happening. And friction opposes opposite the direction of the relative motion, which is not the same thing as motion itself. So kinetic friction just opposes the sliding itself, not the just motion. So this is a misconception. Friction does not oppose motion. Friction opposes relative sliding. And this will come up in some examples later. Usually it just happens that that is the direction of motion that is being opposed. So the relative strength of the friction force between two surfaces actually doesn't depend on things like size or contact area fundamentally. There's a coefficient of friction mu, which characterizes sort of the strength of the frictional interaction. So friction comes microscopically from these sort of imperfections between surfaces. You can think of it as like almost two puzzle pieces fitting together, which happens at the microscopic level. And some surfaces are a better fit for each other than others. And it does turn out that in most cases, these friction coefficients are between 0 and 1, with kinetic friction being less than static friction, which should make sense because that relative sticking together is probably stronger than the just scraping opposition. Again, these are due to microscopic imperfections and forces. So, in addition to this coefficient, which is determined by the surfaces, so the only way to change mu s or mu k is to pick a set of surfaces. So it is not a property of one material, it is a property of the two objects touching. So for example, rubber and ice versus iron and copper. Those would have different coefficients with each other. So in addition to that, the force is determined by the normal force exerted because normal forces are exerted by surfaces. So it makes sense that this force from the surface should also depend on the outward push from the surface. Now, kinetic friction is very straightforward because it's just an equal sign, but static friction has an inequality. So what that means is that static friction does not have a single value. Static friction will take on whatever value it has to oppose the sliding. So for example, if I have a book at rest on a table, static friction doesn't have to work this hard to stop it because I'm not pushing. So there will be no static friction. But if I start pushing on the book, static friction will have to start fighting and fighting and fighting and fighting. This value, mu s times normal force, tells you the max value of static friction. And once you hit that value, that's when the push wins and the object begins to move. So usually we're just going to deal with this as a maximum because we're almost always interested in these like starting to move type cases. But just realize that static friction works as hard as it can until you beat it. And then the object starts moving, and then it's kinetic friction time. So I think we'll just do a nice long form example showing what's happening here. So we have a box of mass 5 kilograms. It's on a horizontal surface. We start pushing it, and there is both a static and kinetic friction coefficient. Again, it is a coefficient, so that is why these are unitless quantities. Because we go back to our formulas, we see that the normal force is in newtons. So since the friction force is also in newtons, we just have a unitless constant in front. Just tells you how many normal forces worth of force you have to push with. Balance friction. So what we are saying is that the box is being pushed to the right with this force. So I initially don't push the box. Then I push the box harder and harder and harder and harder and harder. And then the box finally begins to move, and I just keep pushing with that force. So let's draw and label the forces exerted on the box during each of these intervals. So first of all, this box is going to live on its lovely flat horizontal surface forever. So I will give the same gravitational force, because it is the same box. I will give it the same gravitational force at all times. And I will also give the same normal force at all times, because the box is not falling into the surface. And there's no weird diagonal things happening, so I know that this is going to be a nice clean balance. So now what's happening? Well, it's pushed to the right with a pushing force. And it does not move until t equals t move, and it does increase with value over time. So before the box starts to move, I am definitely pushing it, but the box hasn't moved yet. Why hasn't the box moved? Well, because friction is fighting it. And that would be static friction, because we have not moved yet. That should make sense. I'm trying to push. Think about trying to push something heavy. You can push and it won't move, because static friction says, "Oh, you're pushing? I don't think so. I can beat that." But eventually, at some maximum value, the force is increased to the point where static friction finally loses. So this is actually still static friction at this point. It's just technically the max value of static friction. But then after that, we have defeated static friction, and the box begins to move. And we're still pushing it at the same force. But we're now down to kinetic friction, which we were given in this problem and in almost every problem, that kinetic friction is lower than static friction's max value. So what does this tell us? Well, this tells us originally we have no net force, so we have no acceleration. We have no net force, so we have no acceleration. Here we have a rightward net force, so we have a rightward acceleration. Because again, if I push with as hard as I do to get it to move, well, that's not how hard I have to push to keep it moving at constant speed. I don't have to push that hard, so my push actually wins in this case. All right, what is the maximum value of F push? Well, we see that the maximum value of F push is what gets me to move. So F push is just going to be equal to the max value of static friction, which is equal to mu s times the normal force. And the normal force on the block is just its weight, mg. So now we can just do some computing. So mu s was 0.6. I can already see that I'm getting scared here. The crate is 5 kilograms, so the weight is 50. This is what I'm scared of. Ooh, what is 0.6 times 50? Should just be 30 newtons. 3/5, yeah. So that's the maximum value I push with, because I know that that is what beats static friction. What is the frictional force exerted on the crate at each of the following times? Well, at t equals 0, we know that before the crate starts to move, the push is just balanced by static friction. And at t equals 0, I have not started to push yet, so static friction has nothing to fight. So 0. Static friction does not care because I'm not pushing. What about halfway to the moving time? So if I check my graph here, we see this is a linear graph. So I just need to oppose half of the max pushing force. So once again, static friction is just going to oppose the pushing force. And in this case, I'm pushing not with the maximum 30 newtons I could push with, but I'm just doing half of that due to the linear function. And then at t move, well, at t move, I have gotten the max value of static friction, which we said was 30 newtons. And then what about after t move? So after t move, we are moving. So if we are moving, the frictional force is not static, but it's kinetic. So the formula for kinetic friction, it's not max or anything. It is a set fixed value. If the surfaces are sliding, kinetic friction is just this expression. And normal force is still mg. So our kinetic coefficient, I believe it was 0.2. Yep, 0.2. And the weight mg is still 50. So this would be 10 newtons. And notice that is less, as we expected from our free body diagram, right? Because we said after t move, we should be pushing with that value of 30 newtons, but only experiencing 10 newtons of kinetic friction, so it is less. All right, let's sketch each of these. What is the magnitude of the frictional force exerted on the box? So before we start moving, we're pushing and pushing and pushing and pushing, and static friction is just responding. So we push more and more and more and more and more, and static friction matches us. But then, after that, we have won. So the sliding begins, so it's now kinetic friction, which is constant, and in our case, lower. So we get this discontinuity. We get a nice constant kinetic friction regime that's lower. So we do get this little jump discontinuity. What about the acceleration of the box? Well, not moving, not moving, not moving, not moving, not moving. And then it does begin to move. But notice the net force is constant, so we have a constant acceleration afterwards. Because the pushing force is constantly 30 newtons, and the resistive friction force is always 10 newtons. So we have a constant force, constant acceleration. And what would be the speed of the box? Not moving, not moving, not moving, not moving, not moving. And then we have a constant acceleration, so our velocity goes up by the same amount every second, meaning it is linear. So why do we know this? It's because this is because F net equals constant. So this is because A, which is the slope of this graph, is constant. All right, let's calculate these things now for after the box begins moving. So what is the net force exerted on the box? Well, we said that the net force exerted on anything can be written as the helping the velocity forces minus the hurting the velocity forces. What's helping the box move? Well, that's the push. What's hurting the box's motion or opposing it? That would be kinetic friction. We said the push would be 30 newtons and the kinetic friction was 10 newtons. So the net force would be 20 newtons. So what's the box's acceleration? Well, acceleration, just Newton's second law. Take your net force, divide by the mass, 5 kilograms, and that gets us 4 meters per second per second. Now that we have acceleration, we can find anything else. Calculate the displacement of the box 2 seconds after it begins moving. So, laundry list. Not how you spell suvat. We'll scoot this over. All right, so we want delta x. 2 seconds after it begins moving, so it begins moving. We have its acceleration, and we want it 2 seconds later. So that means VF is the unknown quantity that we don't care about. So the VF-less equation is our good old friend, delta x equals 1/2 AT squared plus V0T. So delta x would be equal to 1/2 times 4 times 2 squared plus 0. And that would be 2 times 4, so 8 meters. Nice clean answer there. So that was a nice sort of just big description of all the things we could ask about static versus kinetic. Now we'll move on. A broom of mass 4 kilograms is being pushed at constant speed. Constant speed. So across a rough floor, so that means we're balanced. And the force is 10 newtons, and it is oriented at 37 degrees with the vertical. So we got a strange looking angle here. We want to draw the forces, and this is a calculate everything question. Well, of course, we have a broom with mass on Earth, so it's got gravitational force. It is being pushed. So I will give it that downward right pushing force. And we're balanced, so we have some forces to deal with here. So vertically, I have 1, 2, 3 units down and a 4th unit down. So I have 4 units down. So I need an extra large normal force up. And it's still not balanced because I have 1, 2 units to the right. So I need a frictional force to the left to balance. And what is it? Well, it's a moving broom, so it's kinetic. All right, now let's calculate everything. First, let's get the horizontal and vertical components of the force pushing the broom. So we need Fx and Fy. So here, I want to show you that sometimes we don't just have the horizontal triangle. Sometimes we get the angle from the vertical. It is no big deal. So how this works is, again, the fundamental rule is that cosine extracts the leg that touches, sine extracts the leg that doesn't touch. And this is honestly just not a right triangle right now. Better. So 37 degrees touches the downward vertical leg. So 10 cosine 37 is actually the vertical leg this time, and 10 sine 37 degrees is the horizontal leg. Again, the rule is the adjacent side is always extracted with cosine, the opposite side is always extracted with sine. So we have the x component is actually given by sine today, and the y component is cosine. It's a 3, 4, 5 triangle. It is a 3, 4, 5 triangle, and the y component is bigger this time because the cos 37 is with the y component. This should be 8 newtons, and this should be 6 newtons. You're never expected to do this in your head, by the way. I get a lot of joy of making my numbers work out like that. All right, always a freebie. What's the weight of the broom? It's just mg. What is mg? 4 kilogram broom, so 40 newtons. What's the normal force exerted on the broom? Well, we haven't needed it yet, so let's bring out our rectangular broom component body. So we have a gravitational force down. We have a down and to the right push. So we have a rightward push, and we have a downward push. Then we have a normal force. Then we have a friction force. So we are given that this is constant speed, so everybody's nice and balanced, which means that the up forces balance the down forces. So the normal force is just going to be equal to Fg, the weight, plus the vertical component. So the weight we said was 40 newtons, and the y component we said was 8 newtons. So our normal force, notice, is larger than the weight of the broom, which makes sense because there's an extra push that the normal force needs to balance. All right, what about the frictional force exerted on the broom? Well, frictional force is given by mu k times normal force, but we don't have mu k because this part actually makes us calculate mu k. So we must be able to figure out what the frictional force is using another method. And just look at our component body. Our component body is telling us that the frictional force is exactly canceling the rightward push because constant speed means that frictional force must be exactly balanced by the pushing. So the frictional force is simply the x component of the push, which was not 6 newtons, I imagine. That seems right to me. So what is the coefficient of kinetic friction? Well, now we can use the only equation that has a friction coefficient in it. So mu k is just going to be the frictional force divided by the normal force. Frictional force was 6 newtons, normal force was 48 newtons. So that's 1 over 8, which is 0.125. Nothings. 0.125 nothings. I had someone do that last year, and I thought it was funny. They'd always answer their mu in nothings. All right. Now we have some more statics to do. We're just changing up the scenario. So now we're actually pushing something against a wall. So a book of mass m is pressed against a wall with force F perpendicular to the wall. The coefficient of static friction needed to remain at rest in the book and the wall is mu1. So to label the forces, so of course we have gravitational force. We're pushing the book into the wall. So there's this sort of pushing force. And then the book is at rest, so we got to do some balancing. So we know that there's definitely a force up, and that is going to be our static friction. Because it's static friction, because the book is at rest, so it's static. And static friction is up because if there is no friction, the book would begin sliding down. So to oppose the sliding, our friction force must be up. And what is opposing my push? Well, normal force always acts out of the surface. So notice if you tilt your head, it can look like just a normal flat horizontal surface. So normal force is just perpendicular to the surface all the time. So if you have a different angle surface, that's okay. Your normal force will just be angled out differently than usual. So this gives us two equalities that we can write. So first, the left and right pushes balance. And second, the up and down pushes balance. So derive an expression for mu1. So we are interested in the minimum coefficient of static friction. So anytime you're looking at these boundary points for friction, we are looking at the max value. So we know that the gravitational force is going to be equal to the maximum possible value that static friction can supply, or else the book would begin to slip. The mass is m, so mg. Max value of static friction is mu s times the normal force. And then according to our force diagram and force balancing, the normal force is just going to serve to balance that into the wall pushing. So mg is equal to mu s times fn, or this minimum coefficient mu1 is just going to be mg divided by the force F. So why does this make sense? Well, if your mass is larger, that would be a larger weight for static friction to have to support. So it makes sense that that goes on top. You need a larger coefficient to support a bigger weight. It also makes sense that force is in the denominator, because if I push harder on the wall pushes harder out. So there's a larger normal force, increasing friction. So that's why that makes sense. And now we got a tricky one where instead I'm actually pushing down and in with that same force F. So draw and label the forces. So what does not change? Literally just this. So now we're pushing with the same force, but we're going down and into the wall. But it is still balanced. So, of course, we know that static friction is still going to balance everything. But now, static friction doesn't just have to balance the weight. Static friction also has to balance part of the push, because part of the pushing is trying to take me down the wall. So I need a large static friction that's up the wall. And then what about the normal force? Well, the normal force, I only got to balance part of the pushing now, so normal force actually goes down, and it's less than the push now. It's only part of the pushing. So this might be a lot easier if we do our component body now. I'll make my book the correct shape here. So we are going to have a downward push from gravity, and part of the push from Y, and part of the push is sending me into the wall. Static friction opposes both of those, and then the normal force opposes that push. So we see that this is an equality we can write. So we see that the X push balances static friction. Nope, that's normal force. I mislabeled it. So we see that we have a balance there. And it's going to bother me that this is not lined up. This is normal force. So quite a bit more complicated than just the three forces here. All right, what do we think about the coefficient? So do we need a bigger friction coefficient or smaller coefficient to stick the book to the wall in this scenario? We got to justify by referencing the differences between the two force diagrams. So this is a hard one. This is one of the harder comparisons I make you do. It's more clear if we look at the diagram. So notice that now we have part of friction. Friction must serve to balance part of the push. So earlier, friction was just balancing the weight itself. Now that didn't change, so it still needs to be balanced. But now you're giving more downward force that friction has to fight. So in scenario 2, you have to supply more friction force than before. But it's technically not that, like, we can't actually stop there because friction also depends on normal force. But the normal force also goes down. So friction force, you get less bang for your buck because the normal force is going down in this scenario because the push, there's less of the push into the wall than before. So you get less normal force too. So what do I mean by that? You're going to see a huge paragraph spawn in right now, but static friction max is equal to mu times Fn. So here's the crux of my argument that I'm going to make down here. In scenario 2, we have to supply a bigger friction force because part of the push is trying to send me down the wall. But also in scenario 2, the normal force is going down. So got lots of things working against mu here. I have to supply more force, but normal force is going down. So this means the mu has to definitely go way up. So mu2, number 150 in the national dex. Mu2 must be bigger than mu1 because you have to supply more force, more static friction, with a lower normal force to help you. Oh yeah, that's a big paragraph. You can read that if you want, but I feel like I just explained it. All right, let's derive an expression for mu2. So we have two force balances that we can write. So we should probably just leave these up here. So first of all, we know that the up forces equal the down forces. So the static friction up has to balance both the gravitational force and the down push. Then the normal force must balance the into the wall push. So we can start working this out now. Because we know that the maximum value of static friction, I gotta fix pen thing came undone. So we know that the maximum value of static friction is equal to that coefficient times the normal force. So this normal force, Fs max, we are saying is going to be supplied in order to balance both the gravitational force, mg, plus the component that is pushing me down. So what is that? Well, let's draw our picture again. So here, the angle theta is touching. So the in-the-wall push is F cos theta, and the down push would be F sine theta. So down push would be F sine theta. What is the normal force? Well, the normal force is just balanced by the into-the-wall push, which we said was F cos theta. So this means that mu2 is equal to mg plus F sine theta divided by F cos theta. Okay. Indicate whether your expression is consistent with your selection. Oh yeah, this is a challenging one. So, we're basically saying, does this really mean that mu2 is bigger? So our expression mu1 was just very simple, mg over f. Mu2 was mg plus f sine theta divided by f cosine theta. So is this consistent? The answer better be yes. So what do we notice? Well, first of all, for mu2, numerator is larger, right? Because our original expression just had mg in the numerator. Our other numerator has mg plus stuff. So the numerator is larger. But that isn't enough because the denominators aren't the same. So how do these compare? Well, also, remember that f cos theta is just a slice of f. It's not the whole thing. So f cos theta is always smaller than f. So not only is the numerator larger, the denominator is also smaller. Denominator is smaller. So mu2 is going to be equal to something that is larger divided by something that is smaller, which means that mu2 is larger than mu1, as expected. Do I really have to say consistent? I should. It's good practice. You do get marked down if you don't say consistent. The check mark should really do it, honestly. So, consistent. Yay. Without deriving anything additional. We love that. We love to not have to derive anything else after this mess. Determine the minimum static friction if we instead apply the force above the horizontal. So, what is going to happen if instead of pushing down into the wall, we push up into the wall? Well, what changes? The only thing that changes is we flip the direction of the Y push to go up. And we've done this before, and we've seen this scenario before where if you flip this sort of symmetry, that usually corresponds to a sign change. So originally we had this expression. So my new expression is just going to be, well, this term represented static friction, and this term represented normal force. So the only thing that changes is static friction now doesn't have to balance the sum of mg and f sine theta, it has to balance the difference. So you could have probably guessed that it is just a simple sign swap, that this is minus. Now, there is like a subtlety here where if the change is too big, it is actually possible that the static friction reverses direction and this needs some absolute value, but this was my intention of the problem, is just watching you sort of go for the sign swap. Wow, that is a hard problem. All right, last thing we'll do is actually way easier. I'm just going to deal with one unbalanced case here, which is when friction slows an object to a stop. And we'll see that when you solve the F equals ma equations, usually the only thing that affects this acceleration is the coefficient. Mass will cancel. We'll see lots of mass canceling and lots of problems in the future because lots of these forces have m's in them, because the friction force has normal force, which lots of times is proportional to mg. So let's do a pretty representative example. A car is traveling at a speed VO. The driver spots a hazard, applying the brakes. The wheels lock, resulting in a force of kinetic friction between the wheels and the ground. Friction with wheels is a whole thing. Just trust me. We're going to use this as a model. So what are the forces? Well, my car exists on Earth, so there's definitely a gravitational force. Is the car falling into the road? I hope not. Normal force up. The car is traveling to the right. The car is traveling to the right, meaning the wheels are sliding to the right relative to the road. So there will be a kinetic friction force due to the sliding that is exerted to the right. I don't want to make this red. I've been making it other colors. So we see that F net is to the left, which means that the acceleration is to the left, which makes sense because the acceleration will be fighting the velocity. So we have two scenarios. We have dry road, where there's a kinetic friction coefficient mu dry, and there is a wet road with a lower kinetic friction coefficient, right? Because wet roads are slipperier, so there's less sticking to the ground. We should compare the distances it takes the car to stop. Now, anyone who's in driver's ed knows the answer to this. It takes more distance to stop on wet or icy road. So why is that? Well, we know that our force of kinetic friction is going to be mu k times normal force. So in each of these cases, it's the same car, so we have the same normal force. But in the case of the dry road, we get a bigger coefficient of friction, so we get a bigger braking force, so we get a bigger braking acceleration, so we get a lower stopping distance. So on the wet roads, this coefficient is lower, so you get less force, so you get less acceleration magnitude, so you get less braking, so you get more distance. Net force is kinetic friction, since there's a smaller coefficient, smaller net force in scenario 2, so you get lower stopping acceleration, so it takes longer to stop. All right, let's find an expression for the stopping distance. So anytime you have distance and speed and things, it's kinematics, so you got to get acceleration first. So we said that my net force is going to be the things helping the car move minus the things opposing the car's motion. So what is helping the car move? Nothing. What is opposing the car's motion? Kinetic friction. So our net force would be 0 minus the kinetic frictional force. And that is just mu k times normal force, which would be negative mu k times mg. And it does say just call this coefficient mu. I have the habit of just always having a subscript. That is a very M-looking mu today. So now we can find the acceleration, because acceleration is just F net divided by M. So negative mu mg divided by M. Everybody brought M to the party. Goodbye. So our acceleration is minus mu times g. And now it's kinematics time, because we've unlocked what we needed. We got the acceleration. We have no time involved here, right? We have distance d, like a delta x. We have v0, which is v0. And we do have an acceleration. So we do have 3 kinematics, no time. The timeless kinematics is the squared velocity equation. So we stop at the end. We're eventually going to be stopped. So 0 squared equals v0 squared plus 2 times negative mu g times d. So 2 mu gd would be equal to v0 squared. So d would be equal to v0 squared divided by 2 mu g. Consistency check. Is this consistent with part B? So where we're asking about dry versus wet roads. Well, yes, it is consistent. Because d is proportional to 1 over mu. So as d increases, as mu increases, we're dividing by a bigger number. So the whole thing goes down. Thus, the dry road stopping distance is less than the wet road stopping distance. Maybe it helps to say that, like, on the wet road, mu goes down. So if the denominator goes down, the stopping distance goes up. All right, ratio, and then we're done. Stopping distance d, determine the new distance d in terms of, or if we double the speed versus double the mass. Well, d was equal to v0 squared over 2 mu g. What happens if we double the initial speed of the car? Well, that's doubling v0. So I double v0, so I multiply it by 2, but that gets squared. Right? All the exponents still apply when you're doing multipliers. So this would be 4d. So this is why they say it's important to maintain a nice legal speed, because as you increase your speed, your stopping distance increases quadratically. So very big changes. What about the mass of the car is doubled? Well, d is independent of m. There's no mass of the car in this expression. So this means the stopping distance is still d. All right, there's our friction.